Good morning, friends. Today we are continuing electrostatics. First point is expression for potential energy. So here see the figure, that is 8.5. Here two electrostatic fields. Due to the source we have plus Q charge placed at origin O and plus Q naught charge, that is the small charge between the point A and B. Work done against the electrostatic force, that is Fe vector, in displacing in the charge Q naught through a small displacement dr square appears as an increase in the potential energy of the system. Therefore, du is equal to Fe vector dot dr vector is equal to minus Fe vector dr. So negative sign indicate that it appears because the displacement dr vector is against the electrostatic force Fe vector. So potential energy delta U is equal to integration from R1 to R2, delta U is equal to integration from R1 to R2 minus Fe vector into dr vector. The electrostatic force, that is Coulomb force, between the two charges separated by a distance r is Fe vector is equal to minus 1 upon 4 pi epsilon naught q into capital Q into Q naught upon R square into R, where R cap is a unit vector in the direction of R vector. Negative sign shows R vector and Fe vector are oppositely directed. For a system of 2-point charge, delta U is equal to integration R1 to R2. Delta U is equal to integration R1 to R2 minus 1 upon 4 pi epsilon naught capital Q into Q naught upon R square into R into dr is equal to minus 1 upon 4 pi epsilon naught Q into Q naught minus 1 upon R into R1 to R2. So 1 up minus get plus minus 1 upon 4 pi epsilon naught Q into Q naught 1 upon R1 minus 1 upon R2 minus 1 upon R1, that is upper limit minus lower limit, R2 minus R1. Instead of R we have to write R2 minus 1 upon R1. Total work done from the point A and B, that is W of AB is equal to delta U in bracket 1 upon 4 pi epsilon naught Q into Q naught 1 upon R1 1 upon R2 minus 1 upon R1. It is convenient to choose infinity to the point of zero potential energy, as electrostatic force is zero, that is R is equal to infinity. Thus, the potential energy of a system of 2 points charges, that is Q1 and Q2, separated by a distance R, we obtain from the above equation by R1 is equal to infinity and R2 is equal to R. It is given by U of R is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R. Unit of potential energy is joule. 1 joule is the energy stored in moving a charge of 1 coulomb through a potential difference of 1 volt. So 1 electron volt is equal to 1.6 into 10 raised to 19 joule. One mega electric volt is equal to 1.6 into 20 minus 22 joule. 1 kappa electric volt is equal to 1.6 into 10 raised to minus 16 joule. Concept of potential, that is UR is equal to 1 upon 4 pi epsilon naught R Q1 Q2 upon R. So Q1 upon 4 pi epsilon naught R Q2 is equal to Q2 upon 4 pi epsilon naught R Q1. So quantity V of R is equal to Q upon 4 pi epsilon naught R depends upon the charge Q and located at a point at a distance R from it. So two charges system, that is UR is equal to V1R Q2 is equal to V2R Q1. So V1R and V2R are the respective potential of charge Q1 and Q2 at a distance R from either. So V is equal to U upon Q, or U is equal to V into Q. So V2 minus V1 is equal to U2 minus U1 upon Q is equal to U2 minus V1, that is dW upon Q, that is work done or change in potential energy per unit. So relation between, next point, relation between electric field and electric potential. Consider the electric field produced by charge plus Q kept at point O. Work done to move a unit positive charge from the point M to N with a distance dx from M. So direction of M along, that is OM vector. Thus the force acting on the unit positive charge in the OM vector, the work done dW is equal to minus F of dx is equal to minus E of dx. The work done on unit positive charge dW is equal to dV is equal to difference of in potential between M and N. dV is equal to minus E dx, or E is equal to minus dV upon dx. Zero potential. The nature of potential is such that its 0 point is arbitrary. This does not mean that the choice of 0 point is insignificant. In case of point charge or localized collection of charges, the 0 point is set at infinity. Thus, the potential at a point A in an electric field is the amount of work done to bring a unit positive charge from infinity to A. Say example, potential at a point A in a space is given as 4 into 10 raised to minus 5 volt. Find the work done in bringing a charge of 3 microcoulomb from infinity to A. Thus the answer depends on the path along which the charge is brought. So first we are going to write the given thing. V at a point A is equal to 4 into 10 raised to 5 volt. Charge Q0 is equal to 3 microcoulomb. Coulomb, we have to microcoulomb converted into coulomb, that is multiplied by 10 raised to minus 6. So work done in bringing the charge from the infinity to the point A is work done infinity is equal to q naught v. Q naught 3 into 10 raised to minus 6 into 4 into 10 raised to 5. So 3 4s are 12, 12 into 10 raised to minus 1, that is 1.2 joule. No, the work done is independent of the path. That is, does the answer depends on the path? No, the work done is independent on the path. Next example, if 120 joule of work is done in carrying a charge of 6 coulomb from a place where the potential is 10 volt and another place where potential V, find V. Given W of AB is equal to 120 joule, Q naught is given 6 coulomb, VA is given 10 volts, VB is equal to V. So VB minus VA is equal to WAB upon Q naught. V minus VB is equal to, we have considered V. Substitute the value of VA, V minus 10 is equal to 120 upon 6, that is 20. V minus 10 is equal to 20, therefore V is equal to 30 volts. Next point, electric potential due to point charge, a dipole and a system of charge. First, electric potential due to a point charge. As seen in above, that is in figure, plus Q is charge located at point O. R is the distance between the point O and A from the origin. Distance between NM is equal to dx. So let M be an intermediate point on the path where OM is equal to x. So F is equal to electrostatic force, that is F is equal to 1 upon 4 pi epsilon naught into Q upon x square. So direction away from the O and along OM, therefore work done dW is equal to minus F dx. So negative sign appears as the displacement is directed opposite to that of force. So work done, W is equal to integration infinity to R minus F of dx is equal to infinity to R minus 1 upon 4 pi epsilon naught Q upon x square dx is equal to minus Q upon 4 pi epsilon naught integration infinity to R x raised to minus 2 dx. So minus Q upon 4 pi epsilon naught integration of x square is minus 1 upon x infinity to x. So Q upon 4 pi epsilon naught 1 upon R minus 1 upon infinity is equal to W is equal to Q upon 4 pi epsilon naught R. By definition, the electrostatic potential at A due to the charge Q, V is equal to W is equal to Q upon 4 pi epsilon naught R. At R is equal to infinity, V is equal to Q upon infinity is equal to 0. See the graph. One more example. A wire is bent in a circle of radius 10 centimeter. It is given a charge of 250 microcoulomb, which spreads on the uniformly. What is the electric potential at the center given? Q is equal to 250 microcoulomb converted into coulomb, that is 250 into 10 raised to minus 6 coulomb. R is equal to 10 centimeters, centimeter converted into meter, that is 0.1 meter. And we are going to find out electric potential, that is V. V is equal to 1 upon 4 pi epsilon naught Q upon R. 1 upon 4 pi, that is the epsilon naught, that is 9 into 10 raised to 9. Q is 250 into 10 raised to minus 6 upon 10 raised to minus 1. So 10 raised to 5, 250 into 9, 2250 into 10 raised to 4, then 2250, so 2.25 into 10 raised to 7 volt. So this much is for today. Tomorrow we will say next point, that is electric potential due to an electric dipole.